Around the world, coastlines are vital for our lives, industry, and civilization. Since the beginning of humanity, these areas have been chosen for settlements, economic exchange, and industrial activity. Unfortunately, these areas are subject to multiple hazards that threaten society and its interests. These hazards include environmental threats like erosion, storms, flooding, and hurricanes. However, when the coast is situated along plate boundaries, additional geohazards come into play: volcanoes, earthquakes, and tsunamis. But while all pose significant risks, earthquakes are the most frequent and impactful hazard. Their sudden and unpredictable nature, coupled with the potential for widespread damage and loss of life, makes them a constant concern for coastal communities. When the coastal area is situated along a diffuse plate boundary characterized by slow deformation, there will be occasional catastrophic events. The northwestern African coast is an example. In contrast, coasts situated along or near highway deformation zones experience frequent hazards. Strong to huge earthquakes occur and directly impact these civilizations. The Japanese coastal area is one of the most active seismic zones globally, experiencing strong earthquakes and consequent tsunamis. This is due to the low-angle subduction between the Pacific plate beneath the Japanese archipelago. Rupture along the subduction plate impacts the onshore part with strong earthquakes and the ocean part by inducing large waves that inundate the coastal area, leading to catastrophic consequences. On March 11, 2011, an earthquake with a magnitude of 9 struck the Japanese coast, leading to a massive tsunami. Recently, on January 1, 2024, another major event with a magnitude of 7.5 struck the western coast of Japan. To understand and prepare for earthquakes hazards in coastal areas, the lessons learned from these two earthquakes are invaluable. Our esteemed guest, Professor Koji Okumura, will delve into this topic at an upcoming conference. Professor Okumura will summarize and explain crucial information regarding the hazards from the 2011 and 2024 earthquakes. He will also discuss the realities of such disaster and their aftermath. By understanding these coastal hazards and learning from past events, we can better prepare for future occurrences and build more resilient coastal communities. This video is brought to you by the Geohazards community group alongside GeoLearn Hub platform on Facebook.
I'm going to talk about 2011 Tohoku and 2024 Noto earthquake because 13 years and 5 hours ago, the Great Tohoku Earthquake occurred. Today is the day of the Tohoku Earthquake, so I must talk about Tohoku Earthquake. But since I think you all know very well about that big event, I talk about the how to forecast and save lives from such hazard, about like Tohoku earthquake. Then I will make general introduction what happened on the New Year Day in Noto, and details about coastal uplift. Okay, and lastly I talk about some mystery about subsidence and uplift. Okay, so just short summary about earthquakes. So for the easy comparison, I show Kobe 1995 and Tohoku 2011, I'm sorry, Noto 2024. As it is shown here, fatalities by earthquake was the greatest in Kobe, 6,000. In Tohoku, among 22,000 fatalities, about 20,000 were drowned in tsunamis. And those who killed by earthquake, by ground shaking before tsunami, is estimated less than 1,000, maybe less than 500. you see very high intensity all in Eastern Japan, but the shaking was mild. So not many people killed by earthquake. So this year, New Year Day, Noto earthquake occurred. Fatalities are so far 255. Again, it's not too many, considering the size of earthquake, magnitude 7.5. So Japan is basically a safe place for earthquake, but in Noto, in many countrysides, old houses, weak houses kill people. So this is a hazard in Noto. And in summary, so Kobe earthquake occurred under big cities on the edge of Quaternary Basin. That increased ground shaking, and shaking was extremely severe. Tohoku earthquake was very large, but it was a distal offshore subduction earthquake. And shaking was mild, but huge tsunamis killed so many people. In Noto, large and proximal offshore earthquake. It caused tsunamis, and the fault is dipping down under the cities on the coast. So the ground motion is very strong. So first I show ground motion because those ground motions kill people. So in comparison, 1995 Kobe, the ground shaking was very strong. PGV, peak ground velocity, 1.5 meter. It was very big. And the blue dots are last year Turkey earthquake, Kahramanmaraş. As you see, very high speed peak ground velocity is recorded. Those killed 50,000 people. In contrast, 2011 Tohoku, these crosses, there are high PGA, like 1G, 2G, but PGV was rather small. So residential houses were not so severely damaged. But in Noto, as you see red dots, high velocity over 100 centimeter per second, as well as large PGA killed so many people. Okay. And also, if you see those velocity response spectrum, there was so many fatalities in Kobe 1995, those black lines. 1 to 2 period very strong. It damages individual housing, not building, houses. In Tohoku earthquake, these peaks, high frequency peaks, they don't damage residential homes or large buildings. So the shaking in Tohoku 2011 were mild. And right side shows Noto earthquake, red lines. The blue line, that is that of Kobe, very strong, severe ground shaking. And shaking at Noto exceeds Kobe at 1 to 2 second period. So the shaking was very hard. Okay, that's all about earthquake hazard. Then I explained about Tohoku tsunami. This is the 2011 Tohoku tsunami. As you see, highest run-up reached 40 meters. And in south, about 10 meter to 20 meter tsunamis. Those killed 20,000 people. And the earthquake occurred, subduction interface, very shallow, very low angle. And slip occurred in this part. So the slip distribution is here, up to 50 meters near hypocenter. And from this slip, the ground deformation, seafloor deformation is modeled. This uplift generated tsunamis. At the same time as the sea, coastline was subsided because of the slip towards the sea. This area will subside. And in this diagram, it is not shown, but there was larger deformation along the trench. That is the most important factor that killed so many people and destroyed nuclear power plant. Sorry, this is a tsunami record. There are 3 points offshore Kamaishi. TM1, TM2, they are pressure gauge. And this is GPS float. So this is time, and this is wave height. And 1447, the earthquake occurred. The small shaking is earthquake shaking. Then tsunami from this area. Epicenter area comes first. Then, after about 10 minutes, pulsive wave come. They came later because they generated near the trench here. So while the wave traveled to here, the first wave, this one, came here. Next, the distal wave came. So if there was no this second pulse, no damage, no nuclear power plant are destroyed. Anyway, so the wave reaches TM1, then TM2, then GPS. The height increases as the sea shallows and speed decreases. Okay, so at the coast, at least 10-meter high wave hit the area. Okay, so this is the various inversion. Teleseismic, strong motion, geodetic, and joint inversion. They don't show the deformation along the trench. Only tsunami inversion requires large slip along the trench. That means the slip was not seismic, maybe rather slow, but big slip occurred along the trench. So this is the generated this pulse, okay? And sorry, this one generated the base part of the tsunamis, okay? So this is tsunami inversion model. And for the near the trench, so the shallow part was not seismic. There was no seismic wave recorded from this part. But if you move this wedge 40 meter on 4-degree dipping thrust plane, the seafloor will go up 2.8 meters. And also some geologists modeled this accretionary wedge extruded. If this one pushed out and uplift this part of the slope, the seafloor will rise about 3.5 meters. So this is the cause of the tsunamis from trench, the second part. Okay, now I go to the coastline, and the geographic view is in southern part. The coastline is uplifted during quaternary. There are marine terraces, and people live under the marine terrace behind the beach bar. They are all washed away. In Sendai, Ishinomaki area, it is not uplifting. There is wide backmarsh coastal plain. So when tsunami came, the tsunami invaded deep into this flat plain. And in north, in Sanrik Rias coast, there are narrow embayment and valley. So naturally, tsunami comes in here, and due to space problem, wave become higher, and run up all the way to the cities and towns. So this is what happened during the tsunamis. And I show tsunami deposit here. In Joban coast, in lowland, there were tsunami deposit because tsunami comes, washes beach sand, deposits them here. The same for Sendai Plain. So later, I talk about tsunami deposit. This is very important to forecast tsunamis. Okay. And so this is tsunami height and damages. So in Joban coast, 1,000 people died because there was no warning, no preparedness. In this area, around Sendai, 7,500 died. We knew about medieval Jogan earthquake, this one. 4-meter run up, 10-meter run up, we knew, but people were not prepared. And in north, they experienced 1986 Sanriku tsunami, the red line. They were prepared, but 2011 tsunami was much bigger than 1896. They are prepared for smaller tsunami. Okay, this diagram shows the open red rectangle shows the fatalities in 1896. Okay. So in this area, they built seawall to prevent 20-meter high tsunamis. But 2011 tsunami came over 20-meter high seawall, but the seawall decreased the power of tsunami. So there are fatalities, those yellow peak, but much smaller than 1896. And this area, both in 1896 and 2011, 1,000 people killed because of development of cities in this area. So in 1896, there are many fishermen living along the coast. They were killed. In 2011, new big cities in lowland was washed away. Okay. And here's the solid red fatalities. We knew about big tsunami, 1869 tsunami, but they were not prepared. because the warning was not set against 869 type tsunami. It was planned to be announced to local people in late 2011. It was late. Okay. So what was 869 tsunamis? So this is, we have historic record, one line, but it tells exactly what happened. No shaking, big tsunamis in lowland Sendai city. Okay, and between 2005 and 2010, geologists in Geological Survey of Japan studied coastal lowland to find out tsunami deposit of 869 Jogan tsunami. And in those red points, they successfully found 869 tsunami deposit. And they showed how far inland tsunami came. For example, here it is about 3 kilometers. In 2011, it went up to 7 kilometers. Still, if people knew about the risks and they escaped before tsunami comes, because Sendai Bay is very shallow. So it took 1 hour after earthquake and before tsunami hit. They have long enough time to evacuate from tsunamis, but they just stood there, being happy for surviving big earthquake. And they didn't know about tsunamis. But anyway, the tsunami limit in 1896 and tsunami limit in 2011 is, in many places, more or less coincide, the same. So this is the geologic data, for example, show 869 tsunami. So this is coastal lowland backmarsh deposit, mostly dark silt and clay. Within it, you can see sand, like this one, and this is volcanic ash. And this N1 sand is here, this green line all the way. They have radiocarbon dates, and this volcanic ash is dated to be 910 CE. So 869 tsunami in Sendai, Ishinomaki area this area was completely reconstructed. And from that geologic data, seismologists modeled tsunami source like this, magnitude 8.4, because there was no tsunami deposit here. Only here we found after 2011. So actual earthquake in 2011 is this one. And 20 meter or more slip, 50 meter or more, magnitude 9. So 2011 was much bigger than modeled 869. But still, if people were prepared for 869, probably 10,000 people survived. So it is very important to know about past earthquake. I'm doing paleoseismology, but tsunami researchers doing paleo-tsunami studies, mostly tsunami deposit. So this case in Tohoku tells importantness of tsunami studies, paleo-tsunami studies. And after 2011, a lot of study is conducted And in 2011, we just didn't know such big earthquake occurs in Tohoku. So we have just modeled at most magnitude 8.2 earthquake, much smaller ones in separate different segments, 5 segments, one by one release energy. Actually, M magnitude 9 ruptured entire this area with one shock in 2011. Okay. So now I move to 2024 New Year Day earthquake in Noto. Okay. This is the area surrounding the Noto earthquake. This is the epicenter. The faults are here. And the Sea of Japan, this sea, the Sea of Japan opened 2 million years ago. At that time, it was a great rift. Yes. And there are many normal faults in this direction to open Japan Sea in present shape. And they stopped moving in Pliocene, and in Quaternary, they were reactivated as reverse fault. Okay, so this is Noto Peninsula, and in 2024, the fault from here to all the way here ruptured about 150 kilometers. We knew all the faults, and we evaluated those faults for tsunami source. But we have not conducted ground shaking forecast for those faults yet. Only for nuclear power plant here, they did a lot of earthquake models, but we don't have any earthquake models, ground shaking models for those faults. So we are hit by an unknown earthquake. Okay, so this part I show general information about earthquake. Those are aftershocks in 10 days after main shock. And those red and blue lines are the seafloor trace of tsunami model fault for the tsunami simulations. Okay, and this part, it is west dipping. The other faults are all dipping south, southeast. Okay, so in central part, you can clearly see landward dipping fault. So people live here, coastline is here. Yes. So very strong ground shaking, severe ground shaking occurred right above the fault plane. And in northeast, the earthquakes are deep. That means shallower part of the fault did not rupture in 2024. That may rupture sometime, but we don't know. We have no information about that. And in west, the aftershocks don't show any fault plane or lineament. It is very difficult to distinguish what structure is responsible for this. This one did not move, we know. But since, as I show you, GPS result, this part of the ground is moving westward, and it stops here. So the stress concentrates near the tip of the westward moving block. That may be the cause of the shallow aftershocks here. And this is source mechanism. Epicenter here, and large slip occurred here, and second largest one here. So most damage came from this asperity. And tsunami generated here, right under the sea. As you see, the source mechanism is pure reverse fault mechanism. And this is another fault model by Asano-san in Kyoto University. So the slip is large in east, but this is deep under the sea. And in the west, it's shallow and just under the cities. Also, this causes damage. And the right diagram shows rupture process from hypocenter to both ends of the fault. So bilateral rupturing. And interesting one is the middle one. This shows displacement. This is made from a strong motion seismogram. So integral of the ground motion will show this ground motion. And so this is the start time, 9 seconds. In 25 seconds, rupture reaches, and in a few seconds, the coastline, the ground was uplifted in those seismogram station. Okay, next is GNSS, ground motion. So you see on shore, mostly westward moving. So reverse fault dipped this direction, and fault movement must be this direction. But on ground, we see mostly westward motion near shore. If you are away from the shore, it is perpendicular to the fault trace, normal, that is normal for reverse faulting. So we think it is not shown by earthquake source mechanism. The fault has strike slip movement, right lateral. This is vertical motion. So along the coastlines, station recorded 1.3 meter uplift. And distal stations show movement towards the source area. I think this is normal for reverse fault. I'm not specialist. And the source fault model based on GNSS shows strike slip component too. Okay. And so this is an important diagram to talk about coastal deformation. This is ALOS-2 satellites SAR interferometry result. This one shows actually this area moved 4 meters towards the satellite, this area 2 meters. So the epicenter is here. So the asperity here and here, large slip occurred, they correspond to the area of large uplift here. It's 4 meters here and almost 0 meter here. And Wajima city is a little small. Okay. And this is pixel offset. As you see, most of them show the similar pattern as GNS in SAR results. Another another pixel offset result by Fukushima-san. This also shows the same as INSAR result. 4 meter here, 0, 1 meter here, 2 meter, like this. Okay. And tsunamis. So the left diagram shows the tsunami run-up height based on the watermarks on ground. Tide gauge on shore recorded less than 1 meter tsunamis only. But in many places, watermarks we can find up to 5 meter here. And 4, 5 meter near the top of Noto Peninsula. We don't have any record here because tide gauge was destroyed and the coast was uplifted 2 to 4 meters. So uplifted ground, tsunami didn't run up there. Okay, so the main topic today is the coastal uplift. Okay. So this used to be a port. The uplift here, I think, is 2 to 3 meters. You see the port and banks protect the port, and those slopes were to raise ships. So the water level was here, the black mark here was the sea level before the earthquake. And this is the largest uplift recorded at the Kaiso, 3.6 meters. So the sea level before earthquake is here. So we know earthquake uplift coastlines. We knew from past results, but this is very surprising. So this is abrasion platform around sea level, plus minus half meter, very flat. And it is now about 2 meters above. So this happened in northern shore of north and west shore of Noto Peninsula. So right diagram shows as a record of 2024 uplift in Kaiso, the second picture, 3.6 meter is here. And it decreased southward very rapidly. This area is, I show you later. This is west coast. So the west termination of fault is somewhere here. This one is 2007 earthquake. And this record is 2007 uplift of 0.4 meters. It was small earthquake. The fault is dipping here and uplifted this area. But important data is this MIS5E, 120,000 year shoreline, is 20 meters here and goes up to 63 meters here. So 2024 uplift here was 0.25 meter. And here it is 5 times larger. 3 to 5 times larger. So the pattern is very similar. We don't have 5E terrace here because of erosion. I think there was higher terraces, but they were eroded. Okay, this is Kaiso. Sorry. And the same, in the same area, this is, previous diagram showed from here to here. Okay. And it was 3.6 meter here. And this diagram shows only 2007 earthquake. A small uplift in a small area. Yes. And Shishikura-san studied 3 past shorelines. And uplift pattern of 2007 and previous 2 uplifts are very much different. The oldest one also different. So many different type of uplift occurs here by earthquakes from different sources. Yes, this is important lesson. Okay. Oop, I must hurry. And this is northern shoreline. Again, Shishikura-san's study shows the entire northern shore and the source fault start from here and all the way go east. Okay. And Shishikura-san's finding was Holocene terraces. Around 6 meter, around 5 meter in green, around 3-4 meters in blue. So their uplift pattern somehow similar to uplift in 2024, especially for those red ones. And also there are sessile, a worm living in mean sea level and uplifted, what we call sessile. Yes, tube worm on the mean sea level. Okay, they showed smaller uplift, maybe from individual faults, and large uplift is caused by total rupture, entire length rupture like 2004. So as you see, this red pattern is very similar to 2024. Okay, this is 5E marine terraces. So marine terrace surrounds the peninsula, and where there is no marine terrace, probably by erosion, there are very steep sea cliffs, no terrace. Okay, anyway, so it is very high here, 120 meter, and decreases the height towards Wajima, and again high here. There is no 5E terrace in Kaiso, but as I told you, this is 3.9 meter in 2024, probably over 100 meter 5E terrace. So the large uplift in 2024 here probably correspond to large high, very high 5E terraces. Unfortunately, they are missing. And this shows a correlation with source fault from here to all the way up. Okay, and also you can correlate the uplift. For example, in this part, rather steep decrease to south. And in this part, rather steep decrease toward south. You can see the same tendency from 5E marine terraces. And this side, obviously, 2024 earthquake did not raise those coastlines. But there must be another sources that raise those coastlines, which will make earthquake hazard also. Okay, so we observed coastal uplift in Noto this year, but the most distinctive coastal uplift is in south of Tokyo, in Boso Peninsula. The plate boundary comes here and go under Mount Fuji and come out here. into Sagami Trough and goes this way. We have 1923, 7008 plate boundary earthquake here. And there are Holocene marine terraces. 4 big terraces up to 30 meters. The terraces are like this: 1923, 7008, 3000, 5000, 72,000. And their altitude: 72,000, 7,200, 5,000, 3,000, 1903, 1923. So large terraces, wide terraces are formed by large earthquakes every 3,000 years. And small steps, they were formed by 1923 type small earthquake. Because we know 1923 from leveling, maximum uplift 2 meters, as I showed before. But from marine terraces, raised shoreline, we can reconstruct 7003 uplift like this, 3 times bigger than 1923. And we can model earthquakes. A ruptured in 1923 Kanto earthquakes. B and C didn't rupture. They ruptured in 1703, probably. And you can find smaller 1923 type earthquake every 500 to 1,000 years. And total rupture of A and B and C, or B and C rupture occurs 2,000 to 3,000 years. So this is our latest reconstruction of the time series. So thus, from marine terraces, we can forecast, reconstruct past earthquake, and reconstruct future earthquakes. Then I come back to Tohoku, because there is another big issue here. That is subsidence. Tohoku coast subsided totally in 2011. But in long term, this coastline is all being uplifted. This coastline is subsiding. This coastline is probably neutral or uplift in north. So 2011 Tohoku earthquake does not explain this pattern of a coastal subsidence and uplift. And this is Fukushima Daiichi nuclear power plant, which was destroyed by 2011 tsunamis completely. And it is located on 5E marine terraces, 50 meters high. But they removed soft sediment, 35 meters, and built nuclear power plant on 15-meter high ground, which was washed by the tsunamis. Okay, so long-term uplift is very clear. But in short term, before, in 40 years, it was subsiding. And only after Tohoku earthquake, this coastline is coming up rather rapidly. And this is 1 year survey result of uplift, 6 millimeter per year, very fast. However, this is transient deformation after 2011 slip. This just compensate, because this uplift pattern is indifferent to regional uplift here, subsidence here, neutral here. So they don't uplift. the coastline. The same things occurs in Hokkaido. This part of the coastline subsided over 50 years, subsided during intraplate subduction earthquake here, like Tohoku. Still, we have, this is terrace height, 30 meter, 50 meter, 6 meter high, 5E terrace. What makes those marine terrace? In Shikoku too, we have uplifted terraces and coseismic uplift here and subsidence here. But this area, Tohoku Basin, is ever subsiding. Why this area uplift? So people just believe thrust raise this part, but some researchers hypothesize thrust fault dipping this direction by oblique subduction is uplifting this part. We still don't know what is the cause of uplift and subsidence. So this is the 2011 uplift offshore generating tsunami, subsidence along the coast. Okay. So this doesn't explain uplift of the coast. And this is idea. If deeper part slips significantly, above that slip, uplift may occur. But since it's deep, the amount of slip must be large. That means very large earthquake in deeper part of Tohoku earthquake. And it occurs right under the cities on the coast, like in Noto. So this may be much worse earthquake hazard. We still don't know what will happen next. Okay, I must stop here. Thank you very much for your attention.